Hello class, in this video we're going to learn how to find missing lengths in similar right triangles. Specifically, right triangles that we get formed by drawing an altitude to the hypotenuse of a right triangle. First, here's a little bit of a refresher, and I'll figure out are these similar first. So you should be checking what the third angle is in these triangles, and here we get 56.3. So these both have 56.3 degrees and a right angle, so those are similar by angle. And similarly, you check that and you get 33.7 degrees. All right. So now we want to figure out what are the unknown lengths of the triangles. So you should be able to write proportions here. And keep in mind that to find the hypotenuses, you might want to think about using Pythagorean theorem. So you're going to figure out what those missing measurements are. So for the length of YZ, you should get 2.25, writing this proportion or something similar. And for the two hypotenuses, you should be using Pythagorean theorem, or you could do Pythagorean theorem and then write proportion, but that's a little bit more work. So you should square root of 13 and the square root of 7.3125. And then part C is just a little explanation of how we solved this problem. So now, what is an altitude? Write down your own definition, and then I'll show you our math definition. So altitude in math is really just another word for the height of something. When we measure something's height, we always go perpendicular to the ground. So that's along the same lines of what altitude means. You go from one vertex to the opposite side perpendicularly. And in the case that you have an obtuse triangle, and the altitude can be outside the triangle, you just have to extend that side that it would hit to form the right angle. So this altitude is actually not inside the triangle. So what happens when we draw an altitude from a right angle from its vertex to the hypotenuse? So BD is an altitude. How many triangles do you see here? How many triangles do you see? Hopefully you said 3. We got the small one, the medium one, and the large one, the whole triangle. So what are the 3 triangles by name? See if you can name them. I'll show you my solution. So we have triangles ABC, ADB, and BDC. There's lots of ways to name them. So now we want to see, do we have similar triangles? This triangle ABC, the large one, is that similar to triangle BDC, the medium one? And the same goes for ABC and AD, the small one. Are they similar? Well, if you look at them, they both have right angles. Each pair, they have right angles, and they share a vertex. So these two statements are both true by angle. So for example, if we're looking at, let's say, ABC as this right angle, and so does BDC. BDC has this right angle. And they both share vertex C. So those are similar by angle. Now the order is important. Is triangle ABC similar to triangle DBC? Well, now if we look at the order, we have ABC, we have this angle, and then the right angle, and then this angle up here. But if we look at the order for DBC, DBC starts with the right angle. And so that right angle isn't congruent to angle A, so that's the incorrect order. So the triangles are the right triangles, the correct triangles. You have to name your vertices in the correct order. So be careful there. And finally, can we say that the medium triangle is similar to the small triangle if you write it in the correct order? And yes, we know that similarity is transitive. So that is true. Same idea here. What's the altitude in this diagram of triangle EFG? The altitude is GH. And what are the 3 similar triangles, keeping the corresponding angles in order? A few correct ways to do this. Here's one, EFG, GFH, and EGH. So in each one, we're going from the small angle to the medium angle to the right angle. And do we get similar triangles? Yes, for the same reasons as before. We can use angle, angle, and transitivity to say that those triangles are all similar to each other. So now that we know they're similar, we can use that to figure out what missing measurements are. So let's look at this right triangle. First, I'd like you to draw an altitude from vertex B to the hypotenuse, and then label the distances they give here appropriately. So they want ADX, they want DC to be Y, and BD to be Z. So hopefully you drew a diagram that looks like this one. Now we want to figure out what the values of X, Y, and Z are. So there's many ways you can go about this. I'm going to show you the way that I think is easiest. And like I said, if I've said in the past, if you can do this a different way, that's easier for you to get the same answer, that's perfectly fine. So I make a table, 3 columns for information and 3 rows. So we want to fill in each piece of information that we know. First, in ABC, we want to figure out what its short leg is, the long leg is, and the hypotenuse. So if you look at triangle ABC, the short leg is 5, the longer leg is 12, and the hypotenuse is 13. I'm going to fill in that information. For ADB, we have X is the shorter leg, Z is the longer leg, and 5 is the hypotenuse. And in triangle BDC, the shorter leg is Z, the longer leg is Y, the hypotenuse is 12. So now we can use this table to easily write proportions because we know these are all similar. So say the ratio of the shorter leg of triangle ABC to its longer leg, that has to be the same as the ratio of the shorter leg to the longer leg of the 2 other triangles. So I'm looking for X first. Well, we have an X right here. Okay, and the only other number we know in triangle ADB is 5. So we have to use the X and the 5 here. Now, if we compare triangle ADB with triangle BDC, we're going to have 2 variables because this would be Z for the shorter leg and that would be 12. So we have to write a proportion using triangle ABC. So we could say something like 5 over 13 is going to be the same as X over 5. And then we apply the cross product. And we divide by 13, and you get 25/13. So now we can fill this information into our table. So here's my new table. It's filled in for X. So now we want to find Y. Same idea. Here's Y, and we know this distance right here is 12. So we use Y and 12. And let's see, we got to use the first triangle because that has known measurements of 12 and 13. So Y divided by 12 has to be the same as 12 divided by 13. Cross product, divide by 13, and you get 144/13. I'm going to fill that in on my table. And finally, to find Z, we have a few different options here. I'll show you one way. I'll show you a few other ways you could have set it up. So I said Z divided by 5 has to be the same as 12 over 13. Apply the cross product, and Z is 60/13. Another proportion you could have written this one. You could have said 25/13 is to Z, as 5 is to 12. I like to avoid the fractions, though, because we had nice integers here. You could have said Z divided by 144/13 equals 5/12. You solve either of these, you will get the exact same answer for Z. Let's try one more. So here's our triangle with its altitude. I called it X for now. And we want to write a similarity statement first. So triangle RST. So let's see, the small angle to the hypotenuse. I'm sorry, small angle to the right angle to the larger angle. So the RST is 2. RUS, right? Small angle, right angle, larger angle, and SUT. When I say larger angle, I mean larger acute angle. It's not larger than the right angle. So fill in the table now. Try that, and I'll show you my table. It should be based on this information. That. There's a little typo here. Okay, and if we fill in our x here for US, we have x in those two positions. So multiple ways to find SU. But in the end, you should get the exact same answer as I get. So try to solve it, and then I'll show you my solution. So I said 36 divided by 39 has to be the same as x divided by 15. Apply the cross product, divide by 39, and you get, it simplifies to 180 over 13. And so SU is 180 over 13. Got a few recap questions for this lesson. So what happens when we draw an altitude from the right angle to the hypotenuse? We end up with similar triangles. What's the relationship between the original triangle and the two similar ones? By angle, we show that they're similar. And how can we use the ratios to find the missing lengths? We read our tables, and we use that to write our proportions. And note that when we use the term shorter leg and longer leg, that doesn't really apply to an isosceles triangle. But we can still use it, the same method. We just wouldn't use the term shorter leg and longer leg. They would just be the legs, and they're congruent. In this lesson, we found out how to find missing lengths of similar right triangles. Thanks for watching this video.